When you're at a stoplight, your car's engine is completely disconnected from its wheels. There's a physical gap in the drivetrain, and yet, power is jumping that gap, flowing through a vortex of swirling oil. Picture two desk fans facing each other on a table. Turn one on, and its breeze starts to spin the blades of the other. That gentle push is exactly what you feel when your car creeps forward in drive. So how does that same gentle system launch your car with real force? And how does it change gears so smoothly you barely even notice? When you sit in drive with your foot on the brake, the engine side spins. The wheel side mostly waits. Oil inside a round metal can moves the force across the gap. The car can idle without stalling. When you ease off the brake, a little push sneaks through the oil. The car rolls forward smoothly. This setup has to solve a tough mix of jobs. It needs to creep in traffic without drama. It needs to pull hard from a stop. It needs to change ratios without a head bob. A manual can do some of this, but not all at once. With a manual, your left foot opens and closes a clutch. During a shift, power is cut, then reapplied. That works, but people are not perfect at timing under load. You cannot hold and grab two places at once. An automatic needs a steady path for torque while it swaps ratios quietly. The device that makes this possible is called a torque converter. It's a sealed, fluid-filled unit shaped like a flattened donut, bolted directly to the back of the engine. Inside, there are three key players. First is the impeller, which is part of the converter's housing and spins with the engine. Second is the turbine, which faces the impeller and is connected to the transmission's input shaft. And sandwiched between them is the cleverest part, the stator, mounted on a special one-way clutch. When the engine runs, the impeller acts like a pump, flinging transmission fluid outward and across the gap. This high-speed fluid strikes the blades of the turbine, forcing it to turn and sending power to the wheels. This idea goes back to German engineer Hermann Futtinger. He patented the fluid coupling in 1905. He added the stator in 1908 and made the true torque converter. That one-way stator is the secret to strong launches. It flips the returning oil so it helps the impeller at low speed. But here is the real genius. It does more than just couple the two sides. It multiplies torque when you need it most. From a standing start, the impeller is spinning fast, but the turbine is barely moving. As the fluid strikes the turbine blades, it gets deflected and flows back toward the center. But now it's trying to spin in the opposite direction of the engine. This is where the stator comes in. It locks on its one-way clutch, and its angled blades catch that backward-flowing oil, redirecting it completely. The fluid now re-enters the impeller already moving in the right direction, giving it a powerful boost. This hydraulic leverage can nearly double or even triple the engine's torque for a moment, giving you that strong, satisfying shove off the line. We're talking a multiplication factor of 1.8 to 2.5, right when you need it. As you gain speed, the turbine catches up to the impeller. The flow straightens out. Now the oil returns without that backward swirl. The stator stops helping and freewheels. That removes drag. Torque multiplication fades toward 1-to-1. Slip goes down. Things feel calm. Each car picks a stall speed to match its engine. Stall speed is the engine RPM where the impeller cannot spin faster without the turbine turning. Typical numbers are around 1,500 to 2,500 RPM. A peppy small engine may like a higher stall. A torquey big engine can use a lower one. The goal is a clean launch at the heart of the torque curve. There is a trade-off. When a converter is not locked, it slips a bit. That waste turns into heat. Under light load, efficiency may be 85 to 95%. Good, but not perfect. So engineers added a lockup clutch inside the converter for cruise. The lockup clutch clamps the turbine to the impeller when speeds match. Now they turn as one. Slip drops to near zero. Heat falls. Fuel use improves. This became common in the late 1970s and the 1980s. Today, cars lock in more than just top gear, and they can blend in and out gently. So that's how power gets to the gearbox smoothly. But how do you get different ratios without the grinding and sliding of manual gears? The answer is the planetary gear set. It's a compact, almost magical arrangement of gears that are always in mesh with each other. It has three main components: a central sun gear, a set of planet gears that orbit the sun, held by a planet carrier, and a large outer ring gear with internal teeth that encloses the whole system. The secret isn't in engaging different gears, but in choosing which part of the set to hold still. By using hydraulic clutches and brake bands to lock one of the three components, you can change which part is the input and which is the output, radically altering the speed and torque that comes out the other side. Try a simple example. Hold the sun still and drive the ring. The carrier turns slower than the input. That is a reduction for pulling power. Now try the flip side. Hold the carrier and drive the sun. The ring spins faster than the input. That is an overdrive for quiet cruising. For reverse, hold a different part and the output simply runs backward. No extra idler needed. Early automatics stacked these sets to make more gears. In 1939, General Motors launched the Hydra Matic with Oldsmobile. It used a fluid coupling, not a true torque converter, plus multiple planetary sets. It shifted without a clutch pedal, and drivers loved the smoothness. Then Paul Ravigneaux pushed it further in 1949. He nested two sun gears and shared a common ring. That compound set made more ratios in less space. Later families built on this. Simpson gear trains used two linked simple sets. Ravigneaux and Lepelletier compound sets power many modern 6-to-10 speed automatics. More ratios, tighter packaging. The smooth, almost imperceptible shifts of a modern automatic come down to incredibly precise hydraulic control. Deep inside the transmission case are several stacks of multi-plate clutches and brakes, usually 4 to 6 of them in total. For any given gear, only 2 of these packs are engaged, one to lock a part of a planetary set, and another to connect a different part to the input or output. This keeps parasitic drag to a minimum. A gear change is simply a perfectly timed handover. As one clutch pack is hydraulically released, another one is applied. The torque path from the engine to the wheels is never broken. The brain behind this timing is the valve body, a complex labyrinth of passages and valves. In older cars, this was a purely hydraulic computer. Today, it's run by computer-controlled solenoids that can modulate fluid pressure with incredible precision, typically between 60 and 200 pounds per square inch. To make shifts faster and smoother, a modern transmission control unit pre-fills the clutch pack for the next gear with a small amount of pressure, so it's ready to engage instantly. The result is what you see in a state-of-the-art unit like the ZF 8-speed transmission. It can perform a full-throttle upshift in about 0.2 of a second, with no interruption in acceleration. One clutch grabs just as the other one gracefully bleeds off its pressure. There is no power gap like you get with a manual. What do you feel from the driver's seat? First, creep. At idle, a little torque leaks through the fluid. Old ads bragged you could stop on a hill without touching a clutch. Take your foot off the brake, and the car inches forward. That is just the fans in oil doing their thing. Next, launch. When you step on it from a stop, the converter hits near stall. The lock stator boosts torque. You surge forward. As speed rises, the turbine catches up. Slip tapers down. The car feels like it hooks up. On a long mountain descent, the rules change. Riding the brakes can make heat. A lower gear raises engine RPM and pump flow. That gives engine braking and better cooling. Many modern automatics will downshift on their own in this case. They may even lock the converter to cut slip and keep heat in check. And the one thing doing all this work is the automatic transmission fluid, or ATF. This is one of the most complex fluids in your car. It's not just oil. It has to act as a hydraulic fluid to operate the clutches, a coolant to carry heat away, and a lubricant for all the spinning gears. It even contains special friction modifiers to ensure the clutches engage smoothly but don't slip. That entire system is powered by a pump driven directly by the torque converter's housing. This means that whenever the engine is running and the car is in gear, even just sitting at idle, the pump is building pressure, readying the control system for that next perfect shift. A typical transmission holds between 6 and 12 liters of this vital fluid, which is constantly circulated to a cooler, usually near the radiator, to shed the immense heat generated by fluid shear and clutch engagement. Not every automatic uses a torque converter. Dual clutch units use 2 clutches and shift like a robot manual. Many belt CVTs change ratio with pulleys and a belt. Many hybrids modify or delete the converter and blend motor torque instead. Designs vary. So do stall speeds and multiplication. The ranges we gave are typical, not a rule. So let's step back and look at the whole picture. There is an entire mechanical ballet happening in a metal case just a few feet from you. A river of oil jumps a gap, gets redirected by a clever one-way stator to multiply the engine's force, and then gets locked solid for efficiency at speed. Meanwhile, a compact solar system of gears, always in mesh, provides every ratio you need, forward and reverse, just by holding one of its members still. Tiny hydraulic clutches and brakes, choreographed by a computer, perform these holds and releases in milliseconds. All of this, spinning at thousands of RPM for hundreds of thousands of miles, just works. That seamless pull you feel isn't magic. It's the quiet triumph of fluid dynamics and planetary physics. If deep dives into the guts of the things we use every day are what you're here for, consider subscribing. We have plenty more on everything from microchips to suspension bridges. Thanks for watching Buildguts. We'll see you in the next one.